Hi, I'm Denise Chairez, member of the Team 7 of the Subject Final Modeling from City University, and today I am going to show you how to analyze a piston head with the software pattern Nastran. The problem description for this exercise is determine if the stress in this typical piston model is low enough for the material to be in the linear elastic region. The piston material is steel with a Young modulus equal 30 times 10 to the 6th power psi, a Poisson ratio equal 0.3, and finally we have a pressure on piston of 1200 psi. First, we have to open Pattern and create a new database. So we go to File, New Database, select the folder we want everything saved, and the name is going to be piston.db. We select OK and make sure that the analysis type is structural and the model dimension is steel. We already have the model for this workshop, so we go to File, Import, click on Files, select Piston XMT, see that is on Model and Parasolic XMT, and click on Apply. When the summary pops up, we click OK. After that, we need to select a smooth shaded view and rotate the piston for a better view. And because we only have the student's license, we can use topology TED4. The input list is solid 1, which means the entire piston. The global edge length is not gonna be automatic, so in value we type 0.5 and then we click on Apply. Here you can see the mesh created. Now we'll create the boundary conditions, starting by the displacement. So, action is on Create, Object Displacement, and type Nodal. The new set name for this is Fits. Then we click on Input Data, and the translations will be 0, 0, 0. Okay? And after we go to Select Application Region. We select Surface on Face and the Select Geometry Entities we are going to be Solid 1.32 and the Solid 1.31. We click Add for each one, OK, and Apply. Now we have to add a pressure with the new set name of piston_pressure. We click on Input Data and on Pressure type 1200. Click OK and after go to the Select Application region. We have to select the top face of the piston. Click Add, OK and Apply. And here you can see the pressure that we created. The next step is to create the material. So we'll go to Properties, Isotropic, and the material name is going to be steel. Now we have to input the properties, so the elastic modulus is 30 times 10 to the 6th power and the Poisson ratio equal 0.3. Click OK and Apply. Now we are going to create the solid. The properties set name is going to be piston, and we have to input the properties. The material will be the steel that we just recently made. Click OK and we have to select the application region. So we select solid 1. Add, OK, and Apply. After that, we need to check the load cases. So we go to the load BCS, load cases, we select default, and we just check that the correct loads are assigned, and click Cancel. Now we are ready to analyze. So we click on Analyze, Analysis Deck, go to Translation Parameters, and in card format select Small. Click OK, and after go to the solution type. Click on Solution Parameters, after click on Results Output Format, and select XDB. Click OK, click again OK, and finally Apply. After that, you need to open Nastran and select the PDF file created from Pattern and run. Nastran will create a XDB file. So again, we need to go to Analyze, select XDB, go to Select Results Files, select piston.xdb, click OK, and apply. Now for a better view, we go home and click on the plot erase icon. Click erase under geometry and OK. So now we can go to our results tab and select a quick plot. The first result must be stress tensor, and the deformation results must be displacements translational. Make sure that the quantity is set to bond misses and click apply, and here we go. After that, we need to go to the form attributes and select show under form and show tile, and finally we click on apply. We need to go to home and click on the plot erase icon again. Click on erase under geometry, OK. Then we go back to results. Click on the French attributes icon, set display to element edge, uncheck show title, and finally click on apply. Here we can see that the stress is well below the limit, so it's in the linear elastic region. And also we can see the critical areas that are under the maximum stress and deformation. Thanks for watching.